Welcome to the third video about Riemannian optimization. Given we have some understanding of what Riemannian geometry is, we'll fill the blank spots to understand how Riemannian optimization works. Before we proceed, we need to understand the difference between gradient and derivative. As I mentioned, loss backward belongs to the cotangent space, but we need tangent space for the exponential map. If you work with Euclidean manifolds, you can forget about Riemannian geometry, complicated math, and use summation and subtraction, whichever you prefer. But if you work with Riemannian manifolds, you need to really take care about it. Fortunately, metric tensor provides us a way to compute tangent vector out of the cotangent vector we get from loss backward. As you remember, metric tensor is a tensor field. It eats two tangent vectors and outputs a scalar as a linear map. We can use partial function for vectors, for tangent vectors, and feed one tangent vector to the metric tensor and fill one spot unfilled. And what we get is a partial function that will take one extra tangent vector and output you a number as a linear map. And that's exactly what cotangent vectors do. So this partial function is a cotangent vector. And you see, at this side, there is a cotangent vector. Loss backward is again a cotangent vector. What we can do out of it? So, this metric tensor can actually be represented as a matrix that will numerically depend on which chart you use to calculate inner products, but its determinant will be always non-zero, and numerically this will be matrix multiplication. This partial function, it's like on one side you have a vector, in between you have matrix, and the rest, the right part, the right vector, is unfilled and waiting, and you can compute the partial matrix multiplication and wait for another vector. And actually, because this metric tensor is just matrix, we can compute the matrix inverse, and in the same way feed one cotangent vector to this inverse metric tensor, and it will output a function that will instead take functions defined on the manifold, and it will be the cotangent, it will be tangent vector. And that's exactly what we need. So computing the inverse of metric tensor will solve us all the problems. Since metric tensor is a matrix, we can use matrix inverse based on chart we choose, numerically invert it, and translate the result of loss backward to the tangent space, and use it for exponential map. This all will be not required whenever our metric tensor is just identity matrix, because its inverse it's the same matrix and it does nothing. That's why in Euclidean space you don't even think about this math. What we would do if we want to implement our own Riemannian atom using geopt. First, as inputs, we have grad the result of loss backward. We have point, torch tensor, and a manifold, for example sphere. And the first step, we want to get Riemannian gradient, the direction of steepest descent, to fit into the exponential map. And we combine the projection and inverse metric tensor matrix multiplication with the gradient at a given point. The next important step, the basic one, is the update. So how do we compute the xt plus 1 out of xt and the gradient? If we are on a Euclidean manifold, we use subtraction and don't really care. But G is from tangent space of xt. Xt belongs to the manifold. But how do we compute addition or subtraction between two objects that belong to the different spaces? That's only the Euclidean space that help us to mix and forget about this math. And this is the special case of Euclidean manifold where exponential map from x towards direction minus g gives us the subtraction. That's what we use to forget about Riemannian geometry in standard Euclidean optimization. For Riemannian case, we need an expression of exponential map from x towards minus g explicitly, or at least some approximation of it, and it is called retraction. So if we're using geopt and want to implement an update in optimizer, we can use one of the implementations for the manifold for exponential map. In some cases, exponential map is not available or very computationally heavy, and we want to use an approximation for exponential map. And its approximation is called retraction. As input to the retraction, you give a point and gradient, and under the scenes, it will compute the correct update, and the new point will lie on the manifold and satisfy all the constraints. So what about adaptive terms and Riemannian optimization? Because we don't want to tune the learning rate each time, and the adaptive term helps to avoid this intensive tuning. And in Euclidean case, as when we have n independent coordinates, we have n independent adaptive terms, and we treat every coordinate separately. And that's only the case when our parallel transport is identity. So we keep the same basis at each tangent space in our Euclidean space. That's luxury, and it allows us to compute adaptive term with second moment just grad pole 2. However, in the Riemannian case, we don't have ideal coordinates that share the parameter space, the momentum space, and everything else between two tangent spaces. For example, in P1 and P2, we have completely different frames, and tangent space do not coincide. We can't use the same coordinate space. Basis that is in this plane is very ambiguous to what's happening here, and parallel transport is not identity. So everything is not that pleasant in the Riemannian case. What would we do in Riemannian case? The only chance to use adaptive terms is to exploit product structure. And product structure is the following. As you see, there are 5 spheres, and the product structure is the case where one manifold is independent of others. When you change coordinates on one manifold and others untouched, you can see that it's the same as independent coordinates, and it acts exactly the same. If you have this product structure, you can compute the adaptive term as in is a squared norm of the gradient. And in Euclidean case, we did this element-wise, and here we do it manifold-wise per each component of the product structure. If we would like to do this in geopt and implementing our own optimizer, we would loop over the point in groups of parameters and compute the component inner of the point and gradient If we would like to do it in geopt, we would loop over the points in the parameter groups. And given a point and its pre-computed gradient, we can compute component inner at point for the gradient. And yes, this component inner will take in account all the product structure you have in your manifold optimization problem. You compute the adaptive term exactly the same way you did it in regular atom in Euclidean case, using the same equations. Another thing we need to also take in account is momentum. Besides, momentum may seem like a vector with a bunch of numbers. It's attached to a point. And at previous iteration, we may have tau, and it might belong to, say, tangent space of t minus 1. And new gradients lie in the new tangent space of xt. After step is complete, we have a new point xt plus 1, and it will be in the new tangent space. But we need to combine the tangent vectors from one space and another space, two tangent spaces at different points. The way to do that is use parallel transport and to fix tangent spaces so that the old momentum is transported to the new place and lies in exactly the space where the new iteration will be performed. Now we are ready to put it all at once. So of course we start with initialization and pick some random point on the manifold. We can use, for example, random method of the manifold, and then initialize Riemannian atom with IMS grad turned on, passing all the parameters you have from your optimization problem. Then you run your favorite neural net, compute loss backward, and store Euclidean gradients in point.grad. After that, we need not Euclidean gradient, we need the steepest descent on the manifold, and we need the inverse of the metric tensor for that. egrad to rgrad method will give you the correct descent direction given Euclidean result from loss backward. Next, we have prepared momentum from the previous iteration tau t minus 1 thanks to parallel transport, and we compute exponential averaging as usual. To update the adaptive term, we need to take into account product structure of the manifold, computing component inner in the same idea as it's done in Euclidean optimization, and compute exponential averaging for the adaptive term. In the end, we make a joint step for fixing the momentum and updating the point using retraction transport combined to the direction of the steepest descent. That's all. Besides, this math is complicated. You can actually use geopt to perform all this optimization. It's available open source, and you can find the links on the first slide.